goals of a radiation safety program are to ensure that the radiation dose to individuals is as low as reasonably achievable and to minimize the potential for accidental exposures. To help us achieve these goals, each of us needs an understanding of the fundamental nature of radiation. In addition, we have to be able to recognize and employ these methods and techniques that we use to keep radiation doses as low as reasonably achievable and to comply with the procedures established to minimize the potential for accidental exposures. To begin the discussion, the fundamental nature of radiation was taught to us a long time ago by the early pioneers. Back before the turn of the century, Röntgen in his laboratory discovered X-rays, and immediately the medical community was anxious to use them because they gave them the capability of doing things that they hadn't been able to do before. Just weeks after Röntgen's announcement, X-rays like this were being used to help surgeons, in this case to remove the shotgun pellets from the hand of an individual who was accidentally shot. Within months of Röntgen's discovery, X-rays were being used throughout the world for medical applications. And within those few months, we began to recognize that there were some hazards to overexposure with X-rays. Also, back in the turn of the century time, Henry Becquerel was able to show that some materials gave off penetrating types of radiations. And it was Madame Curie who dubbed this phenomenon radioactivity, the phenomenon of continuously emitting these penetrating rays. In addition, Ernest Rutherford named these rays for us, and not knowing their fundamental nature, he just selected the first three letters of the Greek alphabet. And he called the positively charged particles alpha particles, the negatively charged particles beta particles, and finally those uncharged rays, gamma rays. Scientists' understanding of the fundamental nature of matter began to improve as physicists were able to determine that the structure of the atom was mainly empty space with most of the mass concentrated in the nucleus in the form of protons and neutrons surrounded by a cloud of orbital electrons. And chemists learned that there were different forms of the same element, and they called them isotopes. They recognized that these different forms of the same element occupied the same space in Mendeleev's periodic table, which is an arrangement of the elements according to their chemical properties. If we look at all of those isotopes that occur in nature and that occupy those 92 squares, we find out that there are hundreds of them. But then if we ask how many other isotopes can be artificially produced by man, we find out that the number swells from hundreds to thousands. So we have literally thousands of different isotopes, many of which are radioactive, and it is that property of radioactivity that we're interested in. And we're really interested fundamentally in three things when it comes to a radioactive isotope. The first thing is the nature of the radiations that escape from that nucleus that's undergoing the change. And we know that those radiations are alpha particles and beta particles and gamma rays. They're the names that Rutherford gave them. But more importantly, the characteristics of those particles is what we're going to use in radiation safety. The alpha particle is relatively non-penetrating in the sense that an alpha particle, by and large, can travel through air about 2 inches. That means in order to be able to detect an alpha particle, you've got to get your detector within 2 inches of the source, or the alpha particle can't traverse the distance in air from the source to the detector. It also means that if you had a source of alpha particles, and those alpha particles being liberated, if they were to strike the surface of the skin, the alpha particle has so little penetrating power that it cannot penetrate through the dead layer of cells that cover the skin of our body. So alpha particles are non-penetrating type of radiation. The beta particles lie a little upscale in terms of penetration, and beta particles from different radioactive materials are able to penetrate down into the layers of the skin to reach the living cells in the next layer down, and even deep enough to reach the germinal layers of the skin where new cells are constantly being formed. But by and large, most beta particles that we encounter from radioactive materials are not penetrating enough to reach deep into the tissues of the body to irradiate the internal organs and structures. The third type of radiation, the gamma rays, they are the most penetrating of the radiations and can reach down into the deeper recesses of the tissues and irradiate the cells and the tissues and the organs deep inside the body. So we can characterize the radiations as non-penetrating, slightly penetrating, and very penetrating. In addition to penetrability of the radiation, we also have to consider the half-life of the material. The half-life of the material is defined as that period of time for half of the material to undergo that process of radioactive decay. And it's a characteristic fingerprint of each of the radioisotopes that we know. The uranium that Madame Curie was working with has a very long half-life. Yet one of the isotopes that she separated from that uranium ore is known as radium-226. Now, that isotope has a half-life that we still consider to be very long, in that it is 1,600 years, but a good deal less than the half-life of the uranium from which it was separated. Back during World War I, a very common industry was what is called the luminizing industry. And during that time, it was common to take a paint that contains fluorescent material and add to that paint a very small amount of radium-226. The rationale being that the bombardment of the radiation from the radium would excite the paint would glow in the dark. And sure enough, many dials and clocks and gauges were painted with this radium-based paint so that they would glow in the dark. This is the hour hand of a clock that was made back in those early days. And even though 50 years have gone by since that radium source was painted onto that hand, we find that a very small fraction of the radium has decayed away. Because in 50 years, only a very small fraction of radium with a half-life of 1,600 years, only a small fraction will decay away. What is left is the radium-226 that has not yet decayed and is decaying actually as we're looking at it. If its half-life is 1,600 years, what it means if we wait until 1,600 years from now, the activity will be half of what we could observe today. If we were then to wait another 1,600 years, the activity would be down to 25%, and then another 1,600 years, 12.5%, and so on. Which means that for that radiation source to decay down to, let's say, levels that are too low to be detected, we would literally have to wait many, many thousands of years. So the half-life is an important consideration in terms of radiation safety, because it tells me that that source is going to remain radioactive for a long period of time. Now, all sources don't have a half-life of 1,600 years. Some have half-lives that are measured in tens of years. Radioactive hydrogen, or tritium, has a half-life a little over 12 years. Some materials have very short half-lives. You could go to the hospital. The technetium-99 metastable that they use in clinical nuclear medicine has a half-life of 6 hours. So half-lives of radioisotopes range from very large values to very small values. And it's important in radiation safety from the protection standpoint. For example, We know that we're going to have to control this source for as long as we're going to be around, and then some, because of its 1,600-year half-life. Yet the technetium at the hospital, all we need to do is leave it in a safe storage area for a relatively short period of time, a matter of, say, a week, and the radioactive decay will have reduced it to an almost indetectable level. The interesting part about radium as a source has to do with the fact that the radium-226 liberates all three kinds of radiations that we've talked about. There are alpha particles streaming out from that pointer, but of course we can't see them because these particles and rays are invisible. There are beta particles that are streaming outwards from it. We can't see those either. And also gamma rays. We know that the senses do not respond to these types of radiations, but we know that they all share one phenomenon that is very important to us, and that is the ability for those particles and rays to cause ionizations. And ionizations are occurring right now in the air surrounding that needle. In the process of ionization, one or more electrons are stripped away from an atom. This creates an ion pair. The previously neutral atom, having lost part of its negative charge, is now positively charged and forms one half of the ion pair. The free electron forms the other half. This process of ionization is the fundamental mechanism that causes biological damage in human tissue. The cells in our body are made up of countless numbers of atoms that chemically combine to form the specific molecules that cells require. Radiation produces damage by ionizing these atoms. Once ionized, the molecule may no longer have the same chemical properties and thus would no longer be able to perform the way it's supposed to. If enough molecules are altered in this manner, the exposed individual may begin to experience the first symptoms of radiation injury. Radium-226 enjoys a special place in our history about the activity of radiation and radioactive materials, in that many years ago it was decided that a nice tribute to Madame Curie would be to describe the activity of any radiation source in a special unit that was called the Curie. A 1 Curie radiation source is one in which 37 billion disintegrations occur per second. This describes the number of atoms that undergo radioactive decay during each second of time. In a 1 millicurie source, 37 million disintegrations occur per second, and a 1 microcurie source, 37,000 disintegrations per second. In addition to knowing something about the activity of the source, the early investigators were interested in knowing something about the radiation that streams from the sources and from the X-ray machines that they used, and they needed a unit to measure that radiation. The first commonly accepted unit of measurement was the Roentgen, named after the scientist who discovered X-rays. The Roentgen is a measure of the number of individual ionizing events that occur in a given volume of air. The Roentgen, however, is only useful in measuring X-ray and gamma ray radiation. The rad is the unit of absorbed dose. This unit was developed to be a measure of the amount of energy actually deposited in the irradiated material for all types of ionizing particles and rays. The unit rad describes the quantity of energy deposited, not necessarily the biological effect it may cause. The rem is the unit of dose equivalent. It was developed to express equivalent biological damage for all types of ionizing radiation. This unit is the product of the total energy deposited in rad multiplied by the quality factor. This means that for a given amount of energy deposited in human tissue, alpha particles and neutrons have the capacity to do more biological damage than X-rays, gamma rays, or beta particles. The quality factor is a mathematical adjustment that compensates for the differences in biological effects caused by the various types of radiation. We use the gamma ray and X-ray as a baseline for comparison. Gamma rays, X-rays, and beta particles have a quality factor of 1. Neutrons have a quality factor of 10, and alpha particles have a quality factor of 20. Remember, that first unit, the Roentgen, is really a unit of the quantity we call exposure, because all it describes is the number of ion pairs that are produced in air by gamma rays and by X-rays. The rad is a unit of absorbed dose, and all it describes is the amount of energy deposited per gram of material. The rem is the unit that we use to describe the radiation dose to an individual. It is an estimate of the biological damage caused by that radiation. Usually, when we speak of ionizing radiation exposure and the dose units in rem, usually, if not stated, we're referring to whole body radiations. And from this position, this distance from that source, we could calculate the radiation dose equivalent in rem that I would receive if I had to sit here and work here for, say, 40 hours a week or 50 weeks in a year. And the amount of that radiation exposure depends upon the amount of radioactivity in the materials with which I'm working. But suppose my job were to take these old dials and gauges and hands from the clock and remove some or all of that radium paint so that we could reuse that particular part. If that were my job and I had to remove that radioactive material, what I'm going to do is scrape a little bit of it off. But before I do, so that I can handle that source and not get any of it on my fingers. Now I'm just going to hold the end of the dial and with the knife scrape a small amount of that radium paint off of the dial. And now I am potentially being exposed by two routes. One from external radiation coming from the radioactive material, striking my body. The other from this loose material that has been scraped off. Suppose that represented all of the material that was taken off of that dial and the dial were clean. It clearly isn't. That's only a very small amount of the activity. We find out that that little bit of contamination, and that's what we call it because it's radioactive material in a place that we don't want it, but that amount of contamination is still significant, and if we remove the end window of the tube, it's pretty clear that there's a lot of radioactivity there, although not so much over here in this corner. Virtually none there. And it's all in the center. We can see the contaminant as little particles. The next question is, are my fingers contaminated? And if we move away from the source, we find out that they do not appear to be. Okay. How about the tool? Is the tool contaminated? Now let's move further away from the source. I get the impression that there's a little contaminant still left on the end of the tool. And as long as I do operations like scraping or grinding or milling, I stir up loose radioactive contamination. In that process of stirring up loose radioactive contamination, I am potentially exposed to internal contamination from the radioactive material itself, from the radium-226 getting into my body. That radioactive material we refer to as contamination, and if if we leave it there, sure enough, it'll get blown all over, and we will have a very difficult job of cleaning it up. So typically what we do is we control that loose contamination as best we can. But that's the next subject. If we think now of the radiation that the worker can be exposed to as either external from the radiation itself or internal by taking up the radioactive material, having the radioactive material be deposited in the body from which it can irradiate the cells and the tissues and the organs of the body, then we really have two modes of radiation exposure to address in our radiation safety program. The next thing that we have to do is to discuss radiation dose limits, and in order to do that, I would feel more comfortable if we could put this trace amount of contaminant in the radioactive waste and dispose of it properly. And the question comes, what is the maximum radiation dose that we can allow workers like myself in occupations like this? What dose can we allow them to receive? And the answer lies in our radiation philosophy, because the answer is as low as reasonably achievable. So the radiation dose that the worker is going to receive from the external irradiation and from any potential internal contamination that would contribute to the dose should be as low as reasonably achievable. However, it shall not exceed the published maximums, and essentially the published maximums are 5 rem per year. Remember now, everyone is exposed to ionizing radiation just because we live on this planet. Just by living on the Earth, each and every one of us is exposed to natural background radiation from cosmic sources bombarding our atmosphere, from radioactive materials in the Earth itself, and from the small amounts of radioactive materials found within our own bodies. This naturally occurring radiation is the major source of radiation exposure to man, and frequently is used as a standard of comparison for exposures to various man-made sources. The level of natural background radiation is normally expressed in units of millirem per year. The level of this background radiation is not the same everywhere. It varies by as much as a factor of 4 from one region to another throughout the United States. This geographical variation is primarily dependent upon the altitude above sea level, which increases the cosmic ray component, and also dependent upon the concentration of radioactive materials in the soil, predominantly uranium, thorium, and the radioactive isotope of potassium, which have been present in the Earth since our solar system was formed. Throughout the United States, this natural background radiation level varies from about 50 millirem per year to about 200 millirem per year, with an average value of about 100 millirem per year. In addition to this natural background radiation, the average person in the United States is exposed to additional man-made sources of radiation, including medical and dental X-rays, fallout from atmospheric weapons testing, release of radioactive material in natural gas mining and milling, nuclear energy, and a group of consumer product sources including television sets, luminous dial watches, smoke detectors, and static eliminators. This average annual radiation dose to the general population is about 200 millirem per year from sources that are a part of our natural and man-made background. Just for illustration purposes, suppose that we were to use a symbol. Let's suppose that this coin represented the amount of ionizing radiation that we all receive from natural sources. And at the same time, remember, we receive about an equal amount of radiation each year from man-made sources, the medical and dental x-rays and what have you. And if each of those represents 100 millirem, we can then say that the total radiation that our population is exposed to is equal to about 200 millirem in a year from natural sources and from man-made sources. How does that amount of radiation compare with the amount of radiation that is likely to cause some biological effects or some acute responses? We can examine that by looking at then what one full rem of radiation would be, and using the same analogy, one rem of radiation would be 10 of these background units. That's one rem. Okay? We've said that by and large the maximum radiation that any of our occupational workers are permitted to receive is essentially 5 rem in a year. That would be 50 of those background units. And let's say that those 50 units were the maximum occupational limit for our workers. 5 rem in a year's time. The next logical question is, how much radiation would it take to, say, cause an individual to feel sick and to get to the point where there's a chance that that individual might die, right at the threshold of the probability of death occurring? Well, 5 rem is much, much too small to cause any response like that. To reach that level of radiation dose, that would be at the threshold of potential death, you'd need that amount of radiation. That's a bag of 2,000 of those background radiation units. And 2,000 of those background radiation units would be required to make the individual sick to the point where there was some chance that he might die. We might ask, well, how much radiation would have to be received all at one time to just make an individual sick and no potential for death? And basically that amount is about half of this bag full, or 100 rem of exposure received all at once, and the individual is likely to feel sick. As it turns out, the 5 rem of radiation and spread over a year is significantly below the levels required for that acute radiation sickness. And indeed, when we start looking at the experience of occupational exposures in our industry, we find that the unit, the rem, is a little large in terms of day-to-day and week-to-week exposures, and 5 rem is much, much too much to describe the radiation dose that most of our occupationally exposed individuals receive. Indeed, we have to go for another unit change and look at smaller fractions of a rem. And for that we use the millirem. Well, if 5 rem is an annual maximum dose, then 5,000 millirem would be the equivalent. And to demonstrate 5,000 millirem, we just have to have our units changed into something smaller. And each one of these then could represent for us a millirem of radiation exposure. And remember, we said earlier that natural background radiation would be 100 of these from natural sources. And then from the man-made radiation exposures that we get, we need another 100 of those. And that our total for the year with no radiation work at all would be like 200 millirem. What do radiation workers receive? Well, if we look at the figures, we find that of the 1,300,000 odd radiation workers in the United States, about half of them receive no radiation exposure that's measurable. The other half receive, on average, from their profession, their occupation, they receive a little over 200 millirem, or an amount equivalent to our natural and our man-made background, plus a little bit. And that can represent for us the average radiation that the workers in our industry receive each year. But of course, remember, that is an average. Some receive less, some receive more. Indeed, if we take the occupational group that receives the largest radiation exposure, those people who work in nuclear power plants, the annual average radiation dose is still counted in the smaller units of millirem and is about 650 millirem per year. If that's a little over 200, their occupational exposure might be that much. And the distinction then between the maximum that's allowable, which is all of these millirem, and the amount that's actually received by even the largest subgroup of our occupational workers, the distinction is because we do follow those practices and techniques that lead to a LARA, or as low as reasonably achievable. And we do that through a variety of mechanisms. We do radiation surveys, and we know the strengths of the sources that we're dealing with. We also document the radiation exposures that the individuals receive by some type of a dosimetry device. And there are many different devices that are available. They are either worn on the exterior clothing or perhaps clipped to the belt. And these devices, which include things like either photographic film or perhaps a thermoluminescent dosimeter, these devices are constantly being exposed to the external radiation that the individuals receive, and periodically they are returned to the laboratory and processed. The number of millirem of exposure is recorded and the badge is reissued. So we are continually monitoring the radiation exposure through a variety of devices. Okay, why then is the radiation dose that our occupational workforce receive so much lower than the maximum limit? The answer to that is the practice of ALARA and the adherence to those procedures and those techniques that tend to reduce radiation exposures. If we think about radiation exposures as being, say, internal and external, as we've discussed, and the little source that we had here earlier, the total external radiation dose that the operator, in this case me, would receive from the sources, that total dose is equal to the dose rate at my position times the length of time that I stay here. So dose is equal to dose rate times time. We have three primary mechanisms that we do use to reduce this radiation dose. The primary mechanisms that we use are time, and in using time, what it means is instead of me sitting here for 40 hours a week with the source in front of me, perhaps I only sit here 10 hours a week. Then my radiation dose would be decreased by a factor of 4. Oftentimes, we can't use that technique, and we have to look to other mechanisms, the second being distance. And by distance, we mean the distance from the source to the individual. If possible, I would like to be located as far away from that source as I can get and still get the job done, because the total amount of radiation that I receive from that source is a function of distance. The mathematics aren't as important as the concept, and we've all seen the concept before. Open up your refrigerator. There's a little 40-watt bulb. It's bright in there. It's bright in there because the light photons don't have very far to go to scatter off the sidewall of the refrigerator or the carton of milk or whatever it is that we're looking for. Take that same 40-watt bulb into your family room and plug it in. Try to read the newspaper. Try to read the newspaper any place other than right underneath the bulb, and it becomes difficult. Take that same 40-watt bulb down to the gymnasium and plug it in as a nightlight. You can barely walk around without stumbling over things, because the further away the light source is from the material that you're trying to see, the less illumination it has. And that drop-off is rapid and pronounced with increasing distances. We call that the inverse square law. If we were to put our source out here again and permit me to do some calculations, we could show that with our detector at a given distance away, we could make the dial read some predetermined number. If we were to double the distance away that we put the probe, we'd find out that the dial would be reading about 1/4 of that number. And that's the inverse square law. Oftentimes, there's only so far that you can get away from the source and still get the job done. But what we might consider as an application of this increase in distance, if in fact I had to keep scraping all of that luminous paint containing the radium off of those dials and gauges, perhaps I could use distance to an advantage by not bringing to the work table a whole box of 1,000 parts at once. I can only work on one at a time. Bring them in groups of 6 or 10 or 12 at a time, and the balance of them leave much further away. That would be a simple application of the use of distance to decrease the radiation dose. Another aspect of that is for individuals who don't have to be close to the source and they're just waiting around to do a job, wait around much further away so that the influence of that increased distance will wind up with the individual waiting around in an area where the radiation level is much, much lower. So we have time and distance. The third phenomenon that we can use to help reduce these doses is shielding. We saw earlier that we put the source in a little lead container, and we know that all the alpha particles are contained, all the beta particles that are coming off can't get through the lead. Most of the gamma rays that come out of that source, we find out will try to penetrate through the lead, and some of them do. We can examine that by using our detector one more time, and if we turn the speaker on so we can hear it, clearly some of the gamma rays from that source are coming through that lead container and interacting with our probe. If we wanted to demonstrate the use of shielding, we could make the container thicker or put this container inside another bigger container. Since we have none right now, we can make use of some of this good shielding material that's on the table right now. Well, let's just listen now for the level that we hear at about that distance. Now, permit me to shield that with heavy, absorbing materials to attenuate more of the gamma rays trying to escape from that source, and put the detector at about the same position, and we find out that a lot fewer of them are able to penetrate through. Eventually, if we put enough of the shielding material around that source and use enough dense material to absorb those gamma rays, we can get the radiation level down to about comparable to background radiation. And remember, even without that source, our instrument is going to respond to the naturally occurring background radiation that is with us all the time. Okay, so shielding is a mechanism of reducing radiation exposure. Obviously, this would not be acceptable because I couldn't get to the material to scrape it. But I could have a small shadow shield built here out of lead and maybe even some lead glass that I could look through and could do the operation. So we can protect individuals using the concepts of time, distance, and shielding. And in each of those cases, the total dose that would be received would be less. With this kind of a job that would entail the use of radioactive materials that are not sealed, and I might add that that's fairly uncommon. Most radiation workers deal with either X-ray machines where you have no radioactive materials and no contamination, or those that deal with sources of radiation, the source is sealed. And loose contamination can't be generated and isn't normally generated, and we prove that by routinely checking the source to ensure that they're not leaking and that the material is being confined. But some few individuals do work with loose radioactive materials, like the removal of the paint from those dials. In addition to protecting the operator from external radiation, what can we do to protect the individual from internal radiation doses? That is, to prevent the radioactive material from getting inside the body. Well, the first thing that comes to mind is inhalation. Now, if one has to scrape those dials, the process of scraping or grinding that material off is likely to generate dust. And that dust will contain that radioactive material. How about the use of a glove box or a hood or some enclosure? The enclosure with the rubber gloves inside, so that the atmosphere where the work is being done is separated from the atmosphere that the operator is breathing. Well, that kind of a glove box or hood arrangement would certainly be employed for a procedure like this. Without that, it would take just a matter of a partial day's work for us to generate more radioactivity in the air in the workplace than would be permitted by our regulations. So we would control the release of those materials to the atmosphere that we breathe. If it were impossible because of the nature of the job to use a hood or a glove box, it may become necessary to protect the respiratory tract of the individual worker via some type of a respirator or a supplied air device or some other respiratory protection. Recognizing that we can't control the airborne contaminants in the space, we then essentially put the worker in the plastic bubble. The next thing that we do is we employ protective clothing. You certainly wouldn't want to be dressed like this and handling loose radioactive materials. Some gets on your hand, you cross-contaminate your arm, you would be a mess by the end of the workday. It's not uncommon for the employer to provide coveralls, booties, rubber gloves, caps, protective devices, and frequently we see the individuals who are characterized as radiation workers dressed out that way. Remember that that clothing offers virtually no protection from the penetrating gamma rays from a lot of sources, but it does provide an easy way for the employer to ensure that the worker does not go home contaminated and contaminate half of the county. It's a mechanism of controlling the radioactive contamination and leaving it at the job site so that those protective clothes and gloves and whatnot can be laundered under controlled conditions and prevent the spread of contamination. So essentially, protection from the loose contamination is protecting the human body against the three major routes of access that these radioactive materials would have. That is, ingestion, inhalation, and absorption through the skin. Okay, with all of these techniques, the techniques for reducing external exposures and internal exposures, the net effect has been that the radiation dose that our workforce receives is a good deal less than the maximum limits. To keep radiation exposures low, the radiation protection manager or health physicist must establish and periodically review those techniques and procedures used to ensure that the radiation dose to individuals is as low as reasonably achievable. And it is equally important that the workers follow those procedures. In the last section, let's just discuss the procedures that we use to minimize the potential for accidental exposures. The fundamental procedure is to follow the regulations of either the Nuclear Regulatory Commission or the regulations of the agreement state for those licensees that are located in an agreement state. And essentially, the rules that are published for us to follow include all of the concepts that we've discussed up to this point, plus some other requirements like the requirement for certain storage and control of radioactive materials in the sense that we certainly wouldn't want to leave them around and then everybody goes home. The janitor comes in or someone else has access to the area and the sources are not controlled. So those things are spelled out in the regulations that we follow, along with some requirements that we haven't discussed, like the requirements for signs and labeling. So far, if you're going to have radioactive materials in a laboratory or in an industrial setting, depending upon the amount of material that's there, and it doesn't take very much, it's likely to be a requirement that we post the area as containing those radioactive materials. And typically, the sign, is the standard yellow and magenta color, and the word caution or danger, radioactive material. Now, when a lot of people look at a sign like this, what they see through the sign is the mushroom cloud and global thermonuclear war, and it's not intended to convey that at all. It's simply a posting, usually on the wall, or perhaps on the door, or both, or on the container that we're storing the materials in, a little reminder that that container has some radioactive materials in it. And it's just to remind primarily the worker that a certain amount of caution and respect is required. The things that we have to do are spelled out in our federal and state regulations, along with the records and reports that we have to keep, the records of all of our dosimetry data that we've collected on the individual workers, the records of all the surveys that we've taken and taken to ensure that we are in fact controlling the materials like we're supposed to be controlling them. So the records and reports are necessary. In addition, specific training has to be provided to our radiation workers. They need to be kept informed of the storage, transfer, and use of radioactive materials in the workplace. They need to be instructed in the risks associated with their occupational exposure, in the precautions and procedures to minimize exposures, and in the purposes and functions of protective devices employed. And indeed, the worker has to know, at least to the extent that it affects the way that he does his job, the contents of the regulations, either from the state or from the NRC. And finally, the whole control mechanism that minimizes these accidental exposures is embellished in what is called a license. Every employer that uses radioactive materials must receive from either the Nuclear Regulatory Commission or that agreement state agency a specific license that spells out in detail all the materials he's allowed to possess, all of the things he is allowed to do with the materials that he possesses, and all of the special requirements over and above what might be published in the regulations that have to be followed in order for that employer to utilize those materials in the workplace. In conclusion, I'd like to think about radiation safety basically then as being a few basic concepts, a good measure of common sense, and really a willing attitude on the part of the worker to comply with those regulations. The smoke detector, which is common in our households, is a good example of the change in our attitude towards ionizing radiation safety today as compared with the dials of 50 years ago. Instead of using radium-226, we shift americium-241. Difference: for equal amounts of activity in the source, the radiation level that you could measure, say at the location of my hand, is about 1/100th of that from the radium. So a tendency towards using those materials that present less of a hazard to the individual. Instead of it just being loosely painted on and able to be easily scraped off, it's in a chamber that has to be virtually destroyed to get into the source itself. And even if you were able to get into the source, you'd have a small piece of metal that, even if you swallowed it, the radiation dose would be minuscule because it would not dissolve in the GI tract. So the chance of exposure is reduced by material selected and the way that it's processed. An effective radiation safety program depends on a firm management commitment, a clear understanding of individual responsibilities at all levels, and a desire to protect individuals from unnecessary radiation exposures. I guess the conclusion is that radiation safety in the workplace really is a balance between excessive fear and indifference. And if we can strike a happy medium between those two extremes, then radiation safety will work for you and for all of us.